Before we cover this next example, let's do a quick recap of the central limit theorem for means. Now remember, there are three main conditions in order to be able to apply this theorem. You have to have your sample of little size n be randomly drawn. It has to be an independent sample, and that can happen one of two ways. First way is that it's independent automatically. For example, you're doing this with replacement, like rolling a die. Or you're taking such a small sample in regards to the entire population, i.e. it's less than 5% of the population, that the little bit you take is close enough to independent of any other little bit. So you're kind of fudging that a little bit. And then the last condition is that the distribution is normal for the population. Now that can either be given to you that you know it's normal, it's written in the instructions somewhere, or you see a normal probability plot, or you can fudge it if your sample size is large enough. So if you have, and in our textbook will just say bigger than 30. 30 is not actually large enough sometimes, and sometimes it's more than enough. It just depends on the problem, but the rule of thumb we're going with in our book is 30. Now, if that's the case and you have those three conditions met, then the following is true. 1, the shape of your distribution of sample means. Now, this is not your population. This is your sample means. How do your X bars vary? They will create their own normal distribution, no matter what the shape was of the population distribution, right? As long as you have either a large sample or your sample population was normal to begin with. Population was normal. Or you have then you also have a center that was equal to the population mean, which is mu, right? And then intriguingly enough, not only will it become normal, even if it wasn't to begin with, but also your spread will get smaller and smaller, because your spread is called your standard error of the mean, and it's sigma, which is your standard deviation, divided by the square root of n, where n is your sample size. So that means that the larger your sample size, the more tightly packed your data set is going to be, because it's hard for a group of 50 people to have an average that's very far from another group of random 50 people. All right, all of this leads us to this example right here. So we have the following figures show three sampling distributions from a population mean that is skewed left, with mu equal to 4.42 and sigma equal to 1.471. One sampling distribution is based on samples of size 4, another is based on samples of size 8, and the other is based on samples of size 12. We're supposed to label the appropriate sample size for each graph and explain. So here's one graph, here's another one, that's graph 2, and there's graph 3. Now none of these are truly normal. And that's because our samples are, if you see right here, it says that the distribution is skewed left. So we know that this is skewed left to begin with, and we don't have samples of size 30 or larger. So in this particular case, we're not getting a large enough sample size to overcome the skewed left. We're starting to see it a little bit here. So what we need to do is figure out which one of these three has the largest sample size and which one has the smallest. So let me type something up real quick. There we have it. So remember what we just said, when you're looking at sampling distributions, in this case we're assuming sample means, then your spread is going to be the standard error of X bar, which is sigma over the square root of n. Now we know sigma is right up here. It was 1.471 right there. So our three spreads are going to change based on our sample size. So let's try n equals, the lowest one we had was 4. So when n equals 4, what's our spread going to be? There we have it. I substituted it in. So when n equals 4, standard error is approximately 1.471, because that's what our sigma is approximately, divided by the square root of 4. Let me grab a calculator. And then let me clear that out. 1.471 divided by square root, which is above your x squared button, 4. So it's about 0.7355. And then we'll repeat this procedure for 8 and 12. So we'll get 3 different spreads. So let me pause you and I'll be right back with those numbers. There we have it. I found all 3 of them. And you can see the calculator work right there. So I just take 1.471 and keep dividing it by different numbers. So think about what this means. The smallest spread is going to actually happen when you have the largest sample size. So, all right, So what we just found was that the smallest spread is the largest sample size. And that means also that the largest spread is the smallest sample size. In other words, n and the standard error are inversely related, which should not be any shock to anybody because that's why n is in the denominator. Algebraically, when you have a value like that in the denominator, it means that the two quantities, in this case standard error and n, are inversely related. When one gets bigger, the other gets smaller, and vice versa. Now, if that's the case, and our larger spread makes our smaller standard error and vice versa, then all we have to do is look at the graphs, figure out which one has the most spread and which one has the least spread. And the word is right there, spread. Spread out, right? So the least spread is kind of obvious. It's graph 2. It's very tightly packed. There's not a lot happening at 3 and at 5.5, right? The far values. So the smallest spread would be graph 2, and that would be n equals 12. Okay, now what about the largest spread? The largest spread is going to be n equals 4, so we know that. Now the question is, what graph is it? So we have to look at 1 and 3. Now you can kind of see it based off of the most extreme values. So if you're going to have more spread, larger spread, you're going to have lots of values over here at the extreme ends of the graph. I purposely drew these so these are all on the same x-axis scale so that we can compare the spread on them. See how there's nothing happen over here at 5.5 and 3.5 is really low, whereas in this one it's much larger. So that shows us graph 1 has got more spread than graph 2, but we already knew that anyway because graph 2 was the smallest. But let's look at graph 3. All right, look at this. We have values over here past 3.0 and past 5.5. That doesn't happen on graph 1. So that means that graph 3 must be the largest spread, and then the medium, Goldilocks if you will, the medium spread is 8, the one in the middle. If you remember the fairy tale Goldilocks and the Three Bears, you know, one's too big, one's too small, and one's just right, right? So the graph 1 is the middle one. Graph in terms of spread, right? It has more spread than the second one, right? Because the second one's really tightly packed, right? Everything's kind of mushed up here into this really tall tower here in the center at 4.5. So graph 2 is really obviously n equals 12 because it has the least amount of spread. Graph 3 has the most amount of spread. There's all sorts of numbers over here on the end, over here on the left at 3.0 and less, and at 5.5 and greater. That makes it so that that one is the graph for n equals 4, and the middle one is the one that's up here at the top. It's got a couple things at 5.5, but not anything past that, and nothing at 3.0 and or lower. So this is the kind of middle of the road graph. So that means that it's the middle of the road sample size, which is n equals 8. All right, so this whole example, before I head into the next one, was just kind of recapping what this spread means and what this formula means when you look at it graphically. The fact that the standard error shrinks depending on your sample size, and that means the larger your sample, the more tightly packed it is. All right, I hope that helps with that sheet of notes. I'll see you back here for more tutorial videos later.